All right, let's dive into one of those classic physics problems, number 1.196 from Irodov's legendary textbook. This one gets at a really fundamental question that, let's be honest, trips up a lot of us. It's all about angular momentum and asks something that sounds simple. Does an object's spin actually change just because you, the person watching it, move to a different spot? Let's figure this out together.
So here it is, the big puzzle. Picture some system of particles, maybe a spinning galaxy or just a couple of balls twirling around each other. Does the amount of spin you measure, what we physicists call angular momentum, change if you just take a few steps to the left? Your gut feeling might be, no way, the object is doing what it's doing, why should it care where I am? But as we're about to find out, the real answer in physics is, well, it's a bit more complicated.
You see, in physics, where you're standing has a formal name. It's your origin. It's the 0 point for all your measurements. And for a quantity like angular momentum, choosing that origin is maybe the most important first step you take. It sets up your entire frame of reference, and it can totally change the number you end up calculating.
Let's just quickly refresh ourselves on the formal definition. The total angular momentum, which we call m, is basically the sum of the spin of all the little pieces of our system. For every single particle, we take its position vector, r, that's an arrow drawn from our origin straight to the particle, and we do a cross product with its linear momentum, p. Now that cross product is a fancy math term, but all it's really doing is measuring how much of that particle's motion is contributing to a rotation around our specific origin point. Then we just add all those little contributions up for the grand total. Okay, so here's the absolute heart of the issue. A particle's momentum, p, is what it is. It doesn't really care where you are. But that position vector, r, oh, it cares. It cares a lot. Because if you move your origin, every single r vector in that big summation changes, right? And if r changes, well, it stands to reason that our total angular momentum m is going to change right along with it. This little r is the whole reason things get tricky. So to tackle the first part of Irodov's problem, what we really need is a kind of universal translator, a translation formula. We need a simple rule that lets us figure out the new angular momentum, let's call it m prime, from a new origin, o prime, if we already know the old angular momentum, m, from our original spot. This is going to save us a ton of work. So here's our mission, plain and simple. The problem tells us that we know two things to start with: the system's total linear momentum, p, and its total angular momentum, m, both measured from some point O. Our job is to find the new angular momentum, m prime, as seen from a different point, O prime. And we'll just say the vector that takes us from our old origin to the new one is r naught. All right, let's roll up our sleeves and build this formula. First step, we have to relate the old position vectors to the new ones. It's just simple geometry. The new vector to a particle, r prime, is just the old vector, r, minus the shift vector, r naught. Easy enough. Step 2. We just write down the definition for our new angular momentum, m prime. It's the sum of all the new position vectors, r prime, crossed with their momentum, p. Step 3 is where the magic happens. We plug our expression for r prime into that definition and expand it out. This gives us two separate sums. And now, step 4, we look at what we've made. And what do you know? That first sum, the sum of r cross p, that's just our original angular momentum, m. And the second term simplifies really nicely into our shift vector, r naught, crossed with the total momentum of the whole system, p. And that brings us right to the finish line. And boom, here it is. This is the solution to the first part of the problem. Our new angular momentum, m prime, is simply the old one, m, minus this little correction term. And that correction term only depends on two things we already know: how we shifted our viewpoint, r naught, and the total linear momentum of the system, p. This is the powerful tool we were looking for. Okay, now that we have our formula, we can ask that second, much deeper question from the problem. When does our viewpoint just not matter at all? What special conditions have to be met for m prime to be the exact same as m, no matter where we decide to stand?
Let's just look at the tool we just built. We want the new guy, m prime, to be identical to the old guy, m. So what part of that equation has to just disappear for that to be true?
Yep, you got it. For m prime to equal m, that whole correction term, the cross product of r naught and p, has to be 0. It has to completely vanish. This is the mathematical key. So the question becomes, when is the cross product of two vectors equal to 0? Now here's the kicker. The problem says this has to be true for any new origin.
That means for any possible shift vector r0 we could possibly dream up. Since we can pick an r0 that points literally anywhere, the only way to guarantee, absolutely guarantee, that that cross product is always 0 is if the other vector in the equation, the total linear momentum p, is itself the 0 vector. There's just no other way. And this condition, that the total momentum has to be 0, isn't just some random mathematical trick. It actually defines one of the most important, most useful concepts in all of mechanics. It defines what we call the center of mass frame. This is it. The center of mass frame is, by definition, that one special, unique reference frame where the total linear momentum of the entire system adds up to 0. You can think of it as riding along with the system's center of mass. So from your point of view, the system as a whole isn't really going anywhere. It might be spinning or vibrating, but it's not traveling. Our math has led us straight to this hugely important idea. And this is why physicists are so obsessed with the center of mass frame. When you look at a system from this special viewpoint, the angular momentum you measure becomes a true, intrinsic property of the object itself. It represents its pure spin, totally separate from the motion of the system flying through space. In this frame, and only in this frame, everybody in the universe will agree on the value of the angular momentum.
So let's wrap this all up into one clear, simple takeaway. We've been through the vector math and the concepts, but it really all boils down to two distinct cases. Here's the bottom line. In the general case, if a system has some net linear momentum, if it's actually moving from point A to point B, then the angular momentum you calculate will absolutely depend on where your origin is. But in that one special case, where the total linear momentum is 0, which is always true in the center of mass frame, then the angular momentum is the same for any origin. It becomes a fundamental property of how the system is spinning internally. And that leaves us with one last kind of mind-bending thought to chew on. If a planet is flying through space, does that mean it has just one angular momentum? Or does it actually possess an infinite number of them, one for every single possible observer and the entire universe? Based on the physics we just worked through, the answer is, yeah, it does. Pretty wild when you think about it. Thanks for digging into this with me.